Okay, so I'm going to talk about covering spaces. I'll give a bunch of examples of covering spaces, then I'll give the definition of a covering space, verify that a couple of those examples satisfy the definition, and leave some others as exercises. Then I'll indicate kind of what the goal of covering spaces is, and give the main result about covering spaces, which in slogan form is just unique path lifting property. So here's some examples of covering spaces. It turns out you've already seen many examples. So for a first example, there's, well, the map from the circle to the circle is given in complex coordinates as unit complex numbers. In this way, z goes to z to the fourth. As a picture, you might draw it as something like this. So it's the map from the circle to the circle that winds around 4 times. That will be an example of a covering space. Here's another example. The two-sphere mapping to RP2. So the unit vectors in R3 mapping to the set of all lines, one-dimensional subvector spaces of R3, given by a span. We've seen this map before. This surjective map is how we endowed RP2 with a topology through the quotient topology construction. Here's another example of a covering space. Ordered configurations of, say, 5 points in the two-dimensional sphere, mapping to unordered configurations of 5 points in the two-dimensional sphere. We've seen this map before. That's how we endowed the codomain with a topology through the quotient topology construction. So this sends P1 to P5, 5 unit vectors in R3, to just the set of cardinality 5 consisting of those 5 unit vectors. Here's another example. R2 coproduct R2. So as a schematic picture, there's a copy of R2. There's another copy of R2. Just 2 abstract planes mapping to R2. That's just the identity map on each cofactor. So it's given by identity map. Through the universal property we've established for the coproduct, to name a continuous map from this to that is just to name a continuous map from each cofactor. And that is just the identity map. So that's an example of a covering space. Here's some more examples. So generalizing this winding one is the fully unwinded version of the circle, but that's just the real numbers mapping to S1, X. Here's another example. Generalizing this last one here is for I, a set, which we regard as a topological space with the discrete topology. And for B, any topological space, then I cross B to B, just given by a projection, covering space. And this will be an example of what's called a trivial covering space. I'll just draw a picture for our next example. So there's some surface. It has 4 holes in it. And here's a surface. It has 2 holes in it. There's a continuous map. How is it given? Well, it evaluates identically. So on this portion here, it's given by gluing this circle to that circle. So imagine taking this, cutting the surface along those 2 circles, and gluing this top result along those 2 circles. The result is that surface with a seam right there. And just do the same for each of these 3 chunks. And those continuous maps on each of these 3 chunks assemble together to give a continuous map here, it turns out. I'm not going to write formulas for this. It's just to give a picture for another example of a covering space. Here's some more examples of covering spaces, and I'll describe them more informally. So imagine the set of all triangles, equilateral triangles. Equilateral meaning all the sides are not just the same, but have unit length, let's say. Equilateral triangles in the plane R2. There's a natural topology to that, you can imagine. It's a quotient topology of pairs of vectors in the plane or something like that. There's another topological space that's equilateral triangles together with a choice of one of the 3 vertices of it, with a selected vertex. So you can obviously forget, so given an equilateral triangle with a selected vertex, you can forget the vertex. The result is an equilateral triangle. And this indicates another example of a covering space. And as a final example, these are instances of what we have maybe would call moduli spaces, because an element in these spaces is something that itself has some geometric interpretation. So here's another such example of a moduli space. It's the Grassmannian of 2 planes in R4 that we've seen in the past. And there's another space that's the set of all not 2-dimensional subvector spaces of R4, but 2-dimensional subvector spaces of R4 together with an orientation on them. Grassmannian of 2 planes in R4, 2 planes that are oriented. And you can forget the orientation to get a map like this. And that's another example of a covering space. Let me check the video to make sure it's working. Okay. I was going to give another example. I guess I will. So there's a wonderful map from the unit vectors in R4 to SO3, the rotations of three-dimensional space. And it's given W, X, Y, Z. It's given like this. 1 minus 2y squared I don't know if that how enlightening that one is. This is a wonderful map, seen more easily through quaternions.